Very good afternoon. Thank you, ma'am, for the introduction. So first of all, I would like to thank the organizer, and especially Professor Patnaik, for the kind invitation, and the entire team who actually arranged this QMAT. It's not that easy to organize a conference with around 600 participants. Is correct? Working? With 600 participants, it's not a matter of joke. Anyway, so congratulations for that. So let me, I'll talk about a system which is named as double perovskites. So perovskites usually has an interesting structure, and one can tune various properties. And so here basically we try to tune the spin-orbit coupling. Also we can see the pressure effect, also the chemical pressure effect, physical pressure effect in some system, and where if you just look at the system where actually iridium is present, so which is basically 5D materials, the strong spin-orbit coupling, and then here you have an element which is titanium, which is basically non-magnetic because 4 plus oxidation state, while the iridium has 4 plus 5D5, and then you have also cobalt 3D. So that means you have a playground with various transition metal elements. And so you can have also combination of 3D, 4D, 3D, 5D, and study the magnetism and the transport properties. That's the idea. So that means I'll first talk about the introduction about these materials, and especially little more in details about the materials which I'm going to talk. And then the experiment point of view, we did basically structural, magnetic, and thermodynamic measurements. And also we did a DFT basically to check their electronic and magnetic properties, both at ambient pressure as well as physical pressure. So if you apply hydrostatic pressure to the system, how these two quantities evolve as a function of pressure. And especially for one system, one end of the, like if you make let's say the x equal to 1, so when you have no iridium, only you have the magnetic element is actually cobalt 2 plus sitting here, so then how much actually the pressure effect you can see here. Okay, so now this is the structure. So as I mentioned, so if you take ABX3, this is a typical structure of the perovskites. And if you just look at, so this is kind of a curtain, so it creates like an the octahedral environment. So X, usually it's mostly oxygen, but it can be also halogen materials. And AB, so one is sitting here at the corner. So if you put one transition metal here, so it like let's say B here, so that means you are actually having the BO6 octahedra. So the magnetic element surrounded by 6 oxygen atoms, and that gives you basically octahedral environment, and that leads to the crystal electric field in the system. Okay, so now this is typically structure, and it's like a you can think it's like a cube here, and in the corner of one of the cubes, so it is surrounded by this 6 oxygens around, and at the center you have these A atoms here. So that is typically a cubic structure basically. And then basically in a cube, but the structure can be different, but it's a cube, and then you just place the atom accordingly. Okay, and now the thing is that, so if you double the unit cell, so that means in case of ABX3, so if you can have A prime, B prime, and X double 6, just you multiplied by 2 times. And of course what is the advantage or disadvantage? Of course disadvantage would be it's very difficult to prepare maybe, because 2 magnetic elements here, or in this side also you can have magnetic elements. But in our target is that usually the A side is long been studied, so we don't want to change A, so that means we keep same A, that means A2. But B and B prime, where usually you have the transition metals, so that means B prime, 2 transition metals, either you can have 3D or 3D 4D, 3D 5D, or whatever combination you would like to have, and then what kind of physical properties you are interested in. And then also we keep the oxygen position here. X is basically oxygen as it is. Okay, so that is what I mentioned. So that means you can have basically a playground of you can study the magnetism, you can study the correlation, that means the Coulomb repulsion U. You can also study, if you have the 5D material, you can have a strong spin-orbit coupling to the system. You can also tune the spin-orbit coupling. So that is how does it look like. It's a double the unit cell. Nevertheless, there are also examples. You can also call it triple perovskite. So that means it would be again multiplied by 3. It will be even complicated and gives you exotic phases. Okay. Okay, so now the point is that if you look at the periodic table, so where we are basically, so if you just see here, so that is basically in our the 3D, here, and that is the 4D, and this is here where you have these 5D elements, and if you look here carefully, so the material class, what the magnetic the elements of the 3D, 4D, 5D, we are talking about the highlighted red marks, the titanium. In our case, actually, it's 4+ oxidation state, gives you basically non-magnetic ground state here, and the cobalt has a magnetic moment, and the iridium, But if you look at the periodic table, usually what it says, the Coulomb repulsion, the U, that means if you put 2 electrons in the same site, so the Coulomb repulsion, they face the amount of extra energy you need to cause, that's the Coulomb repulsion. So usually it increases if you go from the bottom to top. So namely, the 3D materials are having actually the U value is really higher than the 5D. But if you just come from top to bottom, so like from the 3D to 5D, your Coulomb the spin orbit coupling increases. For example, if you have iridium, so has a lot spin orbit coupling more than the cobalt, let's switch in 3D. So now if you just look at, there is also some sort of energy scale is giving in terms of electron volt. So in 3D, usually you have the U of the order of, let's say, 10 electron volt. And as I mentioned, the magnetic atom is surrounded by the oxygen that gives you the crystal electric field, and this is of the order of 2. So the spin orbit coupling is much less. So that is the energy, the hierarchy. But if you take the 5D elements, so there is bit interesting. So if you just see all the energy scales, so they are of the order of 0.5 electron volt, or there may be it's comparable energy scale. So that means they are competing each other. So if you can tune with some external parameters, either by chemical pressure or doping, or sometimes maybe what the previous speaker mentioned about the strain, also you can tune the ground state of the material. Okay. And another interesting point is that, so if you look at the iridium 4+, for example, here, so actually, as I mentioned, if you 4+, if you do the electronic configuration, then you actually have 5d5. So that means 5 electrons in the outer shell. And then if you keep this there in the crystal electric field, environment, so then you have this Eg and T2G. And then basically here, if you add the spin orbit coupling here, because the 5D elements have significant spin orbit coupling, as I mentioned. So that basically you can have 2 states. So that means this 5 electron, if they are in the low spin configuration, provided the delta 0 is much bigger here. So that means you can also have, let's say, because of the spin orbit coupling, you can have J3 by 2 state, where you can accommodate 4 electrons. And then you have 2 electrons in that state, but since you have 5 electrons in the system, so that means you are actually effectively leading with the J effective half, basically. So you have L1 and then J plus half, so that means you can have 2 electrons accommodated here, so that means effectively you have 1 electron sitting in the system. And that actually there is also in this paper, if you look at the PRL, and there is another paper in the science paper, they show also the insulating ground state, and the insulating ground state actually driven by the spin orbit coupling. So that means spin orbit coupling has a significant role in this system. Okay, so now so then talk a little bit about the mode transition, so which is usually driven by the Coulomb repulsion, as I mentioned. So if you just look at the typical the density of states as a function of electron volt. So in this case of probably have a cartoon. Yeah, if you look at if the 2 electrons, if they try to be closer, it depends on what is the interaction state between the W, which is nothing but the bandwidth. If the bandwidth is much bigger than the Coulomb repulsion, so that can be a metallic state. But like you can see, this is the EF, the Fermi level. So then you can excite very quickly, and then you can get the metallicity. However, if you add the Coulomb repulsion, which is much stronger, much bigger, so U is much bigger than the W, this is the bandwidth, and then you actually create a gap at the Fermi level, and that gap is actually gives you some sort of an insulating ground state of the material. Okay. And now in the system, so if you, let's say, in a system where actually you start with the large U, and then the question is that whether can you get this insulating state to a metallic state. Okay, so then what kind of, so that means some sort of you have to close the gap. Okay, so there is one possibility, either you can do chemical pressure as I mentioned, or the physical pressure, like as I mentioned, the W is usually for a metallic system is much stronger than the U. So in case if you can do certain things, that means they come closer, so you can think in terms of their the orbital overlaps the together, so that means the coupling is stronger. So in that case you can apply pressure. So in that way you can actually create, you can close the gap, and then you can get a metallic transition. So this is the interesting thing, the systems what we are interested in. So that means by using hydrostatic pressure, you just have the interatomic distance, you can make it closer, and in that way hopping can be larger, so that in that way electron can hop around and then gives you the metallicity. Okay. So then with that motivation, so if you just look at the structure which I mentioned here in the title, so that means let us study the two N materials. So once if you put X equal to 0, that means you end up with La2, lanthanum, cobalt, iridium, oxygen 6. And if you put X equal to 1, where you get lanthanum 2, cobalt, titanium, oxygen 6. Okay. But if you see here, so there is some literature study actually sometimes back, and they found actually a ferromagnetic like structure, because it's not a universal ferromagnet. I'll show you the data later on. But they saw some transition around 90 Kelvin. And they also expect some and the magnetic and then the magnetic moment actually comes from cobalt 2 plus as well as iridium 2 plus. So they are both giving the magnetic contribution, and they also reported some sort of a gap which is about 0.26 eV, and magnetization also started shows some sort of an non-collinear canted magnetism, but it's not a global ferromagnet, because normal global ferromagnet you expect M versus H. If you do it, you see a saturation. That I'll show you. And then if you take the other material where actually, as I mentioned, the titanium 4 plus having a non-magnetic ground state, so that means the magnetic moment is coming from cobalt 2 plus, which is a little bit easier to study actually, because you have one magnetic element. Okay. And this system is an insulator, and with an Tn around 15 Kelvin, okay, and it has also some sort of gap, enhanced gap, okay. So that means one end of the system you have some sort of a ferromagnet or ferromagnetic like structure, and another end you are having an antiferromagnet, a little bit higher gap. So now the thing is that if you can dope the system, especially here, if you can dope the titanium at the iridium site, let's say, and how the magnetism and the transport properties evolve. So that is the background, okay. And then why you do, as I mentioned, these things I already mentioned. And in fact, another thing, the titanium 4 plus is having, if you look at the periodic table, the size is little smaller than iridium. So in that way, you can also act some chemical pressure to the system. So if you take the unit cell, the volume would be little less. That also I will show. So that means that, and then in the same fashion, so that means, so if you keep on increasing the titanium at the iridium side, of course the spin-orbit coupling, which was more in the iridium, so that you can also dilute the system, that means you can also set how you can control the spin-orbit coupling, the system. Okay, so now this is so we prepared the material, so it is X equal to Z, that means we are talking about only the LCIO, that means lanthanum 2, cobalt, iridium, oxygen 6. And actually they form a monoclinic structure with the space group number 14, P21 by N, and there are different elements, that means you have, if you look at little structures, that means cobalt, oxygen 6 octahedra, so cobalt is somehow sitting at the center, you don't see, and then the oxygens are the red ones, and then you have actually the, here the iridium, oxygen here, so that means iridium, oxygen 6 octahedra, and then it goes again, if you just go, and then the center, it's nothing but the lanthanum sitting. That is how the structure. And if you look at the structure, one more important thing that is also important, so these octahedra somehow a little bit tilted. So they are not like per 180 degree, they are not very linear. So but that matters because this angle matters. Because if they are perfectly 180 degree, then the exchange path here would be 180 degree. But if not, they are around 150 degree or so. So that means their exchange path will also be different, and that also give you that, like when you talk about magnetism or transport, the properties can be also different. So anyway, so we did the XRD, that looks quite good, and then we did the magnetization, okay. And the magnetization, what we did, so if you just look at the blue curve here, this is at X equal to 0. And that is what I meant. This look like a ferromagnet because the moment is almost zero, and then the moment as soon as you arrive to the Tc or the critical temperature, then you see that the magnetic moment starts to arise. Okay. However, and then there is some sort of, and that is also typical for ferromagnet. Usually, for you see a bifurcation from the Fc and the field cool and the ZFC curve. Okay. Now I just take the magnetization here, the M versus H, but constant temperature. So that means when you are below the Tc, then you try to do the MH curve. Okay. Then if you do it here, then what you see, so the magnetization here, the blue curve at x equal to 0, it's measured at 2 Kelvin, just very way below to the compared to the critical temperature. Then actually you see it is not a perfectly saturation. So we measured up to maybe here up to 7 Tesla. And then actually it's still if you could measure even higher field, it's not really parallel to the x-axis, or namely the field axis, which is typically the signature for a global ferromagnet. So that means it is not a strictly a ferromagnet, and that when you do the calculation, that also get to know. So that's why I told it's a ferromagnetic like, it's not a perfect ferromagnet. And then but if you take x equal to 1, which is the other end, which is a typical antiferromagnet, you see the magnetic moment below the transition temperature around 15 Kelvin, it's the magnetic moment, it starts to go towards 0. So that means the magnetic moment somehow try to cancel each other. Okay, but then that is also not a perfect ideal antiferromagnet. Otherwise, then you would get actually T tends to 0. The magnetic moment should go to 0. But then what happened in between temperature? So in between the concentration. So if you keep on increasing the x, so what happens if you can keep on increasing the x? Actually, you see the change of the Tc to the lower temperature. That is also expected because it goes to the lower temperature. And then also we studied the Curie-Weiss temperature. You know that Curie-Weiss temperature gives you the interaction strength between the ferromagnet or the antiferromagnet. That also we could study a bit. I think there is also some table which is listed in the paper. You can look in details. But the moment it starts to go to the antiferromagnet, so one of the ideas is that whether we can find some critical concentration at which the system is going from ferromagnet to the antiferromagnet. I didn't do anything. Okay, so the antiferromagnet, but we didn't find because we assumed that something, because after this one it's very tricky because you prepare every small concentration and then you do a measurement. Okay, do a measurement. Okay, so but probably it's somehow close to that one. But nevertheless, we just go on. So basically, what we can say that even if you see the MH curve, so there also you can see the loop size also getting reduced as you increase the x value, and when x equal to 1. Which like antiferromagnet, which typically looks like as you increase the field, it's just linear increase and there is no hysteresis. Okay, so now we did some more things. So now if you are, so that means the chemical pressure has some significant effect to the system. Now we try to check in one of the site, let's say x equal to 0, then we try to give some physical pressure to the system, and namely x equal to 0, which is the LCIO, we have the cobalt and iridium. Then we apply the hydrostatic pressure to the system and placed in a squid magnetometer. And then what happens, so what you can see, that is the inset, we try to check just to the derivative, so that to check whether there is a significant effect up to 2 GPa in the system. 2 GPa pressure. So nevertheless, there is some increment here. Also, we try to understand, and then there is a little bit increase in the Tc as you increase the pressure. Just to increase the pressure means again you increase the interactions or the exchange path of the materials. Okay, so now then what we found, it's around 4 Kelvin per GPa. So that means if you have 2 GPa, then you expect around maybe 7 or 8 Kelvin per GPa. So of course, if you have an even higher pressure, which is practically challenging, then you can in fact have even lower temperature. Okay, so now the thing is that we did also with thermodynamics, and just to cross check what we are doing is correct or not. So that means you can do, this is a parameter, it's called thermal expansion. So what you can do the expansivity. So that means you take a sample, you apply some temperature, then usually it contracts or expands, then from there you can calculate the thermal expansion coefficient, and then you can do also heat capacity, the specific heat measurements, and then there also you can just give a heat pulse and then try to measure the temperature. And if it's a thermodynamic phase transition, you usually also see around that 100 Kelvin, you see also some very small anomaly though, and you can see there is some special trick applied. So it's called equal area construction. So that basically energy, the entropy conservation, and then you can calculate called entropy, the called and phase relation, and from there at ambient pressure, these are measurements done at ambient pressure, you can predict when P tends to 0, if you apply pressure to the system, how much TC you can expect to change, and that we calculated, and that is somehow consistent with the experiment which we have done really under pressure. Okay, so now and from this pressure experiment we try to calculate one parameter which is called the piezo-magnetic effect, and what it does basically, so basically what we did, so if you just look at here at above TC, so the magnetization curves are almost on the top of each other. Yeah, so that means what we did, so you can subtract the delta M from this, like you take above 150 Kelvin where the system is completely in the paramagnetic regime, and then you subtract this one, that means magnetization, and then you plot as a function of pressure, and they show some sort of a linear linear behavior. That means we measured, I showed for 3 curves, and then but there are many other temperatures you can do, and once you do this one, you can calculate one parameter from the slope of this one. So you can look this Q is called this piezo-magnetic tensor, and then you can do that. And then if you see, then you try to plot within the error bar, you also see some effect at the phase transition, that means 110 Kelvin. And so that means the system has, and the piezo-magnetic response, what it tells, basically you have some sort of linear increase in the magnetization value as you increase the pressure for constant temperatures. And so now now we did also a little bit on the calculation in the DFT, just to understand. So if you change the doping, how your magnetic and the transport properties change. Okay. So now this is the magnetic structure. So magnetic structure is not available. So one has to do the neutron. We don't have that data. So what we did actually, we try to give different configuration here, the spin configuration. So these are the cobalt and the corresponding iridium configuration. That is important. And then what we found, this is the configuration gives you the lowest minimum energy state of the system. Okay. So then what we did, the total DOS in the system, density of states, and especially for 3 particular concentration. Also we have some more data here, and what you can see here, so at x equal to 0, as I mentioned, it is quite consistent with the what literature you have available, like red curve, which is around 0.2 EV gap, and when you have x equal to 1, you get something around close to 1 EV, and if you have in between this, it is somehow reducing almost 50%. That is also expected. That's quite good. And then also we did a bit of the partial density of states. So that means you can just take different individual atoms, how the density of states they look like. And there also what we found, that magnetic moment also reduced by 50% on the system. And then also you can check the transport, how they are changing. And then also we try to see if there may be the exchange path between the cobalt, oxygen, iridium, there's changing, and that leads you the magnetic, the reduction of the magnetic moment in the system. So now I go to the other extreme. I take maybe 2-3 minutes here. So the other end, that when you have the x equal to 1, so we did some more calculation. First of all, it's an antiferromagnet. You can see, and there you do the Curie-Weiss temperature, you get a Curie-Weiss temperature of minus 50 Kelvin, strong antiferromagnetic interaction. And there is some literature also we found, they also did sometimes back, around 10 years back. So they get some resistivity they measured, also very high resistance. You can see it's of the order of 10 power, more than 7 ohm per centimeter here. And they also, from that they estimated the gap value is 1.02 EV. So now with that, we try to simulate also, try to do the DFT to understand. And first of all, what we did, so that I just give you the results. So when you do the DFT without the correlation, so that means we get some value. GGA is called generalized gradient approximation, but that doesn't actually tells you what you get from the experiment. So that means there is certain value of U is needed, and the moment we add U equal to around 2 electron volt, then actually the value which is get 1.01 electron volt, and this is quite consistent with the experiment. And the moment what we find, that is basically the moment is coming from cobalt 2 plus, and cobalt 2 plus gives you basically the D7 electron. And then if the system is in high spin state, then you get 2.54 Bohr magneton, and this is exactly what we got also from the calculation. And as I mentioned, titanium has also zero magnetic moment, but nevertheless we try to give some the U value, does it change, but it's not the case. Okay, now what happened, we apply the pressure to the system, and that's a beautiful phase diagram we plotted. So I just highlight 2 points here. So if you just look at the blue data points here, the star, the green one, which is basically plotted the gap. So if you apply the pressure to the system, that's by the way, it's a theoretical pressure, like you take a cell and you try to squeeze, and then what you get, so basically as you apply the pressure, at some point around 40 GPa, very high pressure, the system is actually going to the metallic state, 0, and so that means there is a system is going to the insulated to the metallic phase. Okay, and at the same time another parameter is also interesting. If you say the cobalt moment, it's somehow normalized with the maximum field, and there is also at the same point the magnetic moment also drastically changes at the same temperature, same pressure point. And then what we and we did also some more to check at different pressure points how the partial density of states actually changes in the material, and what we found actually, so that means if you take the 0 pressure point and the 42 where exactly the phase transition, metal insulator transition happening, and then what we found, the system is going to from insulator to metallic phase, and also there is an accompanied by the spin state transition. The system is going from a high spin state to the low spin state. And this is some sort of a level diagram, if you can understand how the system goes to the low spin state. Okay. So with that, I would like to come to my conclusion. So that means I showed a system, basically a double perovskite system, where you can tune the magnetism as well as the transport properties. The various ways you can tune the chemical pressure as well as physical pressure to the system, and you can also study the magnetism as well as the transport properties, and you can also tune the spin orbit coupling to the system. So there are 2 papers which published, you can have a detailed look, and these are the people started by my first the PhD student who is currently a postdoc at somewhere Finland, and who started, and then there's another one, Vinita, who is actually continuing the work, and there are a few people who actually helped us in various measurements, cultivation group, Dr. Subhadeep Datta, and some measurements were done also at IIT Mandi. So with that, I would like to thank you for your attention.
The session is now open for question.
In the image curves around h equal to 0, there is a jump in the magnetism value.
Correct.
Is it for metamagnetic behavior or something else?
We try to understand, because that is also in the literature they reported, they call there are 2 sublattice mismatch. It can be a metamagnetic, but it's not very consistent. It's also a bit of sample dependency, you know.
For x equal to 0, there is no jump.
X equal to 0 we didn't say, but in the literature it is there actually. But so it depends also, it's a bit subtle, you know, sometimes the effect is not much. The moment you cross the at field 0, so some sort of maybe a metamagnetic, but it's not yet very clear. Because in our case we don't see, in fact, for all the samples, you know.
Is there any other measurement to specify that whether it is metamagnetic behavior or not?
For a field 0, so I don't know. So for in this case we didn't do.
Hi, very nice to meet you. So I have a question actually regarding your phasor dependent measurement.
Correct.
So what you have showed, you have done a competition study on the phasor, so which basically. So how do you validate experimentally? So do you able to see the same thing in experimental field? And how do you do the experiment?
Correct. So that's a good question. In fact, so of course to go to that high pressure, it's a bit challenging, like 40 GPa. So what we planned, but it's not yet successful. What we are seeing, that if someone could prepare a high field, high pressure synthesis, so that means you prepare the material at high pressure. There are some techniques available. Then you can do an ambient pressure resistivity, let's say. But we haven't done so. But that can be But one measurement which I showed at x equal to 0, that we could go up to 2 GPa, but that is much less than the what is.
No, I know some people do phasor dependent Raman measurement. So like in between the 2 diamond tip, they put the material and they take the Raman mode change and other things. Do you think it will help?
It may help, but as far as magnetism is concerned, or the transport, that we may not get the
parameters.
Correct. That's what we are expecting. Yeah.
Just to add a comment that in high pressure you cannot do this calculation because the surface is not a one oppenheimer kind of thing. So the simple one oppenheimer approximation will not work here. So you will have come across anharmonic effects and so on. So I think that's more complicated. But I want to understand how you choose this U equal to 2 EV, because you have certain fraction of
Correct.
SR and some other components. So once you change the X values, so I don't think that one you can ensure that you will.
So for the this system, for the x equal to 1, what we did very simple. So what we did, so of course you keep on, we have an experimental, the value,
Yeah.
the moment you see the moment you don't have any u value, then of course the gap value which is c, which is quite less compared, then you keep on increasing the value, and then we try to get a value which is compared to the experiment. That is what we choose for the x equal to 1, there. But in other cases also we did, that is a very recent study, we also keep on changing the u values, and to see how it is there. But of course when you go from insulating to metal phase, of course the moment you have larger u, so one has to apply a lot more pressure to get the metallic state, because the Coulomb repulsion is small.
Since you are an experimentalist also, so I was wondering that if you are doing XPS, from there you can actually calculate the U value, and if you are using that U value here in this calculation, that will possibly make more sense.
I see.
Rather than just
Right.
using 2 EV and keep on increasing it, because then you cannot ensure that the exact amount of this localization will really work. for the
That is
system.
that's an important.
That's possibly a better. Anyways, that's
Thank you.
Otherwise you talk time.